My name is Thierry Oppikofer. I'm a geologist from my studies, specialized in natural hazards, and I'm working with landslides since now nearly 20 years. I did my PhD at the University of Lausanne, specialized in remote sensing and especially digital elevation models, but also laser scanning and other remote sensing techniques. Now I work for the company Terranum, which is a spin-off of the University of Lausanne, founded in 2011. And we are also specialized mostly in natural hazards, from hydrological hazards to geological hazards, landslides, and so on. And now in the past 4 or 5 years, we have been extensively working with Earth observation data, mostly satellite data for INSAR analysis of ground motions of landslide active areas. The presentation, my colleague Jean-Philippe Mallet from the University of Strasbourg, he was supposed to join and give the first part of the presentation, but unfortunately had some technical issues, and I'm not sure if he will be able to join now or later. So I have to improvise a little bit on the first part of the presentation, so my apologies for that. In today's presentation, I will give you first a brief overview of the main challenges related to landslide hazard and risk assessment and how we can use Earth observation data and services to handle handle those issues. I am going to present 2 initiatives that ESA has launched the past years to deal with landslide hazards and using EO data. So it's the EO for Alps Landslides project and the Digital Twin of Alps project. I'm going to present the geohazards exploitation platform, which allows the users to access the EO data and perform analysis themselves. I'm going to present some of those services dedicated for landslide studies before finishing with 2 operational use cases, one being the INSA ground motion maps for landslide monitoring, and the other is related to forecasting of shallow landslides. Landslides, as you probably know, are global phenomena which can occur in nearly all mountain areas all over the world and lead to severe consequences in case of a catastrophic failure of a landslide, with fatalities that can occur, socio-economic consequences, and also the different constraints that go along with it to deal with the landslide problems in land use planning, for example. As you probably may know, there are many different types of landslides, broad variety in terms of size, velocity, mechanism, material involved, and so on. And we also deal with many different factors or external triggering factors that can lead to these landslides. So we have, on one hand, we have earthquakes or hydrological extreme events, meteorological extreme events like typhoons and so on, that can, in one single event, trigger hundreds to thousands of landslides. But they may also occur on a more slow basis, on a more regular basis, with less extreme triggering factors. All in all, still after many decades of landslide studies now, we still have the problem that they are quite often to predict, and even still often difficult to detect before they occur. So that's where the Earth observation data they come into play. And so typically questions that we need to answer is what type of landslides can occur? Where can they occur? How can they, or how they are behaving, how they are moving? And are we able to say when the landslide might occur? So this is typically some of the applications that we can envision where we can use Earth observation data to help to answer those questions, or find clues at least to answer those questions. Looking now at the initiatives that the European Space Agency has funded these past years, the first application is the EU4Alps Landslides project, where quite a large consortium of universities, private consultant companies, EU data processing specialists, and others were involved to foster the use of Earth observation data for landslide studies. In order to do so, we have put into place different services that are accessible on the geohazards exploitation platform, which I'm going to present afterwards. And we also involved a large panel of public authorities and other stakeholders responsible for landslide risk management during the entire process of developing those services and testing those services, in order that the products or the services that we provide, that they match the expectations of the practitioners. The other initiative, which I'm going to talk about today, is the Digital Twin of Alps project, which is an ongoing project, where again we have a different consortium of stakeholders from Italy, France, Switzerland, and Austria and Slovenia, so covering more or less the entire Alpine range, with the aim for this digital twin of the Alps is to make a digital reproduction of natural systems that exist in the real world. Our project in the digital twin of Alps is to demonstrate how we can produce such a digital twin using up-to-date EO data and adapted processing algorithms for different natural processes in the Alps. So we are dealing on one hand with a topic called disaster risk management. So it's more the hazard and risk topics related to landslides and floods that we will talk about. But we also have more from the hydrology part, management of water resources, where we have different products and services that are available on the platform. And I think some of those topics related to soil moisture, droughts, and so on, I think you have seen during the past days. In order to achieve this digital reproduction of the natural phenomena, we use a combination of Earth observation data, physical models, but also in situ measurements to make this most realistic representation. Later on in one of the use cases, I'm going to present an example from the Swiss Alps. The geohazards exploitation platform has been launched now a few years ago as an online platform where the users can register and are able to directly access to the satellite Earth observation data. So you have the whole archive of Sentinel-1 and Sentinel-2 imagery and so on. Also the other satellites, but they are a little bit less useful for our geohazards applications. And you have a whole series of processing services that allow you directly online to work with those Earth observation data and produce maps and other analysis relevant for landslide hazard and risk studies. So the platform is very powerful because it allows you also to access directly the data and also the processing of the data. So the whole processing services, they are carried out online using cloud resources. So which has the advantage that the user does not have to have on its own a very large infrastructure or computation infrastructure to do the processing of satellite data himself. In the following slides, I'm going to present now some of those services that are available on the geohazards exploitation platform and that are relevant for landslide studies. One of the first service is to typically after a large storm or hurricane or also after an earthquake, for example, is to rapidly be able to map all the landslides that have occurred during that event. Therefore, we use a service which is called Aladdin, which is a change detection algorithm using a RAS classification algorithm where you automatically map all the landslides that have occurred between two satellite images. So if there's a satellite image before the event and one after the event, and you can, by giving a small training sample, you can afterwards automatically at the regional scale delimit all the landslides, all the landslide activity that has occurred between those two scenes. This afterwards, largely it's an automatic approach, so it also needs to have some visual validation of the detected landslides to confirm, is it really a landslide or is it just the light in the scene that changes, or is it some other deposits that can be interpreted as landslide deposits? But it allows to very quickly give an overview of all the landslides that have occurred after a crisis, for example. The way it is done, I'm going to simplify this a little bit. It's based on this training sample that the user has to manually digitize the landslide that he sees in some areas, and then afterwards you extend that information to the whole study area. The current service that runs on geohazards exploitation platform, it is adapted to Sentinel-2 and Landsat 8 satellite data, so with a resolution of about 10 meters. There are other services dealing with higher resolution data, which are also available, but those need then satellite data, which are not readily available on the JET platform. So you could upload your own satellite imagery, spot images or Pleiad images, for example, and then work with those data sets. This is typically some results also from Haiti that has been affected first in 2001 for 2021, first by an earthquake, and then a few weeks later there was a hurricane which triggered thousands of landslides that have been efficiently mapped by this Aladdin approach. Another service that uses optical satellite imagery is the GDM-OP service. And in opposite to the previous service, the Aladdin service, where we only have one image before and one image after, here we use an approach where we use a stack of images. So we have a whole time series of covering 6-7 years of satellite data, and we combine all those images together in order to make a deformation analysis. And it uses more or less the deformation that is visible over time for fast-moving landslides that you can track over time in different satellite images. And this gives already a spatial map of the ground deformation, where you clearly can see areas that move faster compared to other areas. For those individual measurement points, afterwards you can also extract the time series in deformation in north-south direction and east-west direction, or combined as a 2D deformation vector. So this is one of the ground motion mapping techniques that works very well for very fast moving landslides, let's say several meters of movement per year you can measure with that technique. Another technique for ground deformation measurements are the INSAR techniques. You probably have already heard, and I'm not going too much into the technical details because that would fill a whole lesson for itself. The INSAR data, so they use the radar satellite imagery instead of the optical imagery that we used before. But we use a kind of a similar approach where we also combine a large stack of images, satellite scenes, covering 5, 6, 7 years of data to analyze the average displacement rates and time series for well reflecting points. Here on the GRS adaptation platform, you have different services that allow you to do such INSAR analysis. We have the PS bus service, which is more a surface approach. And we have another algorithm, which is the permanent scatterers interferometry approach in snapping PSI, where compared to the S-bus, where we have more surface areas, here we have individual measurement points. Those images, they show the same area. It's a town in French Alps which is constructed on a landslide and which causes logically important issues or major issues for the local communities. And yeah, I'm sorry here, I don't really, I think I have no idea what this slide means. It's still my colleague Jean-Philippe that should have presented that, so I unfortunately have to skip it. The final service that I'm going to talk about from the GD on the geohazards exploitation platform is a service that allows afterwards to analyze more in detail the results from INSAR analysis or from the optical image, the GDM OptSlide service, where you can afterwards try to correlate in time and in space the different movement patterns that you have from INSAR data. So here, for example, in these INSAR data, you see here the different velocities of the displacement. And when you look at the time series, you can observe different trends, which you can try to classify automatically. So either a linear trend or an acceleration trend, or you have some bilinear trends with a change in deformation pattern when it's faster and then slower, or it can be opposite too. And here we have this time result service, which allows you to load the results from your INSAR analysis or your GDM opt analysis and to extract this or to classify the time series into these different patterns, which allows afterwards to distinguish areas of a landslide. Here we have this moving area where you see different behaviors. Here more an acceleration behavior in the upper part and a linear pattern in the lower part, for example. Then coming to the first use case, where as part of the EO4Alps landslide project, we to obtain an INSAR data set for large parts of the Italian, French, and Swiss Alps, created by Tre Altamira, which is a private company specialized in INSAR analysis. And they have their algorithms QuasAR, which can be considered probably one of the best algorithms that exist presently on the market. In INSAR data, you probably know that you have the different satellites that move in either ascending orbit or descending orbit. And for the INSAR, this is important because when you're in ascending mode, the satellite looks more it always looks to the right side. So in ascending mode, you're looking to the east. So you're sensible to movements that go to the east. When in descending mode, the satellite looks to the west and is thus more sensible to movements in westward direction. But we can combine those two information to obtain a sort of deformation vector in east-west direction and in vertical direction. It's also important to know that one of the limitations of INSAR is that it's not sensitive to movements in north-south direction, unfortunately, due to the configuration of the satellite orbits. And also in heavily vegetated areas, it's difficult or it's nearly impossible to get some signals. Here a brief overview of the data set that we have for Switzerland, where you can see here some clear hotspots of areas with fast movements compared to others. So we have here this is valleys with some of the most famous mountains. You have the Matterhorn, and yeah, so the entire southern side of the valley, we have a lot of landslide activity or a lot of movement registered in those data sets. But you see also some other hotspots in other areas. Just one example how it looks like. This is one of the major landslides that have been detected, where we see differences in displacement velocity with higher velocities in the top and lower decreasing velocities towards the toe of the land at the bottom. And you see again in the bottom where there is vegetation, there is forest cover, so here we don't get any movements. There is also an area here where we don't see any displacement, because here, in fact, the landslides or the landslide is so fast that it exceeds the velocity that can be measured with INSAR. So typically, INSAR has an upper threshold of about 5 to 10 centimeters per year that can be measured with that technique. Another example where we see a large rock slide here, also in valleys, that moves also with several centimeters per year towards the southeast. Here we see also another problem that the wall is so steep that the radar signal is partly hidden by the steepness of the terrain. That's why we don't have a better coverage in that area here. So you see there are some limitations about what the INSAR can detect from the geometry and also the vegetation cover. I'm going to skip that example to speed up the process a little bit. Here another example along the Ledge Glacier also in the Swiss Alps, where we see that there is some large landslide activity on both sides of the glacier related to glacier retreat. And here again, one of the fast-moving landslides, the most flu rock slide in the Swiss Alps, which would be here. It's again fast-moving, so it exceeds the velocity that can be measured with INSAR data. The next example that I'm going to present a little bit more in detail is a complex rock slide at the Pointe des Savoirs. There you see here the different the active area of the rock slide, where we have different limestone that make up this section. And you see here on the other pictures, there's quite a complex pattern with different parts moving in different directions. This is something that we were going to see nicely only on the basis of INSAR data. So here you have two images. On the left hand, you see the ascending data set, so where the satellite looks towards the east. So we will mostly see movements on the southeast facing slope. This is what you see here. So we have here the entire area is formed by a sort of crest or a ridge, and you have parts of the ridge that move towards the southeast, which you nicely see here. And if you look at the descending data set where we look to the east, to the west, we see also on the northwestern side of the ridge, we also have some major landslide activities. If we're going to combine now those data sets together and also integrate a little bit the morphology that we see for the different landslides, we can define different compartments that move with that can be separated based on the morphology, but also on the INSAR data with different displacement velocities and directions. What we did here for these different compartments, or for each compartment, I'm going to focus here on 3 compartments, the blue one and the orange one that lie behind it, and the green one here, which is on the northwest facing slope. And we have extracted the average displacement velocities for those different compartments for the whole time series from 2015 to 2022. And we see fairly slow displacement rates of 1 millimeter, 3 millimeters, 4 millimeters per year, up to 6 millimeters here in the descending data set, and so on. So it's rather at the lower limit of what you can detect with INSAR data. But that was also one of the challenges of this study. What we did afterwards is to combine both the ascending and the descending data, and we projected these vectors on the expected sliding direction. So here we assume that the sliding will occur mostly in the average direction of the slope, which is quite a fair hypothesis. And use this hypothesis allows us to extract not only a 2D vector, but then afterwards even to combine this information to a 3D vector in the slope direction. So this has the advantage that we can now see that we have different compartments. So we have here at front with about less than 2 millimeters per year and a relatively shallow angle, so it's only 25 degrees steep. But we have a section here in the back, which is a little bit fast moving, and it's also going steeper down. And this information we can use and combine it with some other observations about the structures and the geological setting of the landslide, where we can afterwards interpret a possible mechanism for this complex rock slab deformation. Also on the opposite side here on the northwestern flank, we see a similar movement. We have a section in the back, which is moving 6 millimeters per year with a very steep angle, 73 degrees steep, so it's mostly subsidence. But the area located in front of that section is moving at a more shallow angle of 38 degrees. So again, this could be interpreted afterwards in terms of landslide mechanism. The second example I'm going to present is part of the Digital Twin of Alps initiative, where we used where we made an operational forecasting system for shallow landslides. So it is more landslides that occur in soils, and not in rocks as before, but in soils, and often they are only a few meters thick. But as you can see here on this picture, they can still cause some severe disruption to infrastructure and even loss of life. In the framework of this Digital Twin of Alps, we have produced an automated service to forecast for the next 3 days areas that are likely or possible to lead to landslides. In order to do so, we have 3 main processing steps. So first we create a static map of all the areas where the geological and land use conditions are favorable for landslides, which is a so-called susceptibility map. It does more or less indicate all the areas that could lead to landslides, provided that you have enough water inflow or earthquakes as triggering factors. The second part is to forecast afterward which source areas are likely to fail given the current soil moisture conditions and also the current weather forecast for the next 3 days. So this is illustrated here. So ideally that you have a forecast service which says, okay, amongst all those areas that are susceptible to lead to landslides, those red areas, they are prone to lead to a failure within the next few days. And afterwards, once we know which areas are likely to release, then we can assess if they release, how far will they travel? And this is something that we also do in the third step, using a code flow called FLOWR for propagation modeling of those shallow landslides. This is how it looks like in the platform Digital Twin of Alps. I will share the link after, where you can explore yourself. So this is typically the static map of landslide source areas, which differ with different colors, indicating how likely or how unfavorable geological and slope conditions are to lead to landsliding. In the second step afterwards, we use the weather forecast for the next 3 days to assess how likely how likely it is that the landslide will release because of those forecasted precipitations. And here, so we use the freely available metadata set, which is quite a coarse resolution, so it's about 1 kilometer pixel size approximately. And if the forecasted precipitations they exceed a given threshold or a predefined threshold, then we will say all the source areas that lie in those areas, they are likely to fail, and they could lead to landslides. So here, this was from August this year, where we had quite a severe weather situation over the Swiss Alps. So that's why mostly all landslide source areas from the static map were highlighted as potential release areas. And then afterwards, we do the propagation modeling of those in order to highlight the potential conflict areas with man-made infrastructure. To sum up, as you know, and probably also have seen now with my presentation, the Earth observation data is now more and more used for natural hazards assessment, both using optical multispectral imagery, but also radar imagery. I have shown examples from initiatives that ESA has launched and funded these past years to foster the use of satellite data in society in general. And we are convinced that EO-based services and products will be more and more used. And it is therefore important that different public authorities, private companies, and research institutions are also aware of those possibilities, but also of the limitations of the EO data and products, as I've briefly mentioned in my talk in today's presentation. While we have been focusing mostly on landslides today, logically similar approaches can also work for other natural hazards, earthquakes, volcanoes, but also other topics really more related to water resources, for example, or to glacier and permafrost monitoring. As part of the EO4 Alps project, we had quite some outreach activities to different stakeholders, public administration, private consultant companies, and so on, and the research institutions. And we also have prepared a certain number of documents that are available for you if you want to start working with Earth observation data for natural hazards. So typically we have here we have a link for a YouTube for a webinar on a webinar that we did a few months ago, organized by the GRS Exploitation Platform, where we were focusing on monitoring landslides from space. So you see also some other examples in that video. On the chat platform itself, there is quite a thorough documentation of different processing services that are available. So you see we have here the GDM slide is mentioned. We have the Aladdin services. We have Snappy services for INSAR and so on. And there is more or less a step-by-step description of how to use these services and how to make your own processing. Also part of the GRS exploitation platform and the EO4 Alps Landslides project, we have also made some training material with some where we analyze the different services that are available, and we state which services are appropriate for which type of activity, or which scale of analysis, and so on, and how suited they are for the different use cases that you might have. Logically, in the end, if you have any questions, you feel free to ask them either now or to contact me or my colleague using our email, or to look at these websites, either the EO4Alps/landslides.eu for the EO4 Alps Landslide project, or the digitaltwinofalps.com for the Digital Twin of Alps project. And I hope to have given you a brief overview of what is possible to do with Earth observation data for landslide hazard assessment. And I thank you for your attention.